Hey everyone, hope you're all having a really nice weekend so far. This video is about U-substitution and specifically about how to do U-substitution mentally because U-substitution comes up quite a bit in any calculus class. It is, I think, probably by far the most used integration technique out of all the techniques we can expect to learn in Calc 1. So what is U-substitution anyway? Thought it would be nice to do a quick review. So U-substitution applies whenever we're faced with an integral kind of like this, where we have one function that's the clear outer function, we'll call the function u, and then we have another function that is the clear inner function, we'll call that v. So u and v are just two different functions. The function u depends on the function v. So we can see that this is what we call a composition of functions. We have one function of another function. So instead of, for example, having f of x or u of x, we have u of v. We have u of another function. V is going to be the input of the other function. So we have, and then we want to multiply that by the derivative of v. And we're just going to call that dv. So an example of a problem like that would be something like this, where we have maybe square root of x squared. So in this case, we can clearly see that the outer function would be the radical. The radical kind of extends over everything, and then our inner function would be whatever appears underneath the radical. So the inner function would have to be x squared. So we have a clear u in this case. U would have to be the square root function, and then v, of course, would have to be x squared. So now we have to find the derivative of v. We have to find the derivative of x squared, so of course that's going to be 2x dx. Take the derivative of anything involving x, we're going to get a dx as part of the derivative when we do the separation of variables. So in this situation, it's easy to take the derivative, it's easy to take the antiderivative using our U-substitution technique. So I recommend you go back and watch some of the U-substitution videos I have on my channel. If you want to have maybe a better understanding of how it works, maybe you're not too good at it, maybe you've never seen U-sub before, it's a really good idea to get just kind of a really good intuitive understanding of how it works because it is widely used, very widely used in calc. So let's get into the strategy that I want to talk about, the main topic of this video. It is just a quick and effective U-substitution techniques. Maybe get to the point where we can do it in our heads and save some time when we're solving really big, complex problems later on. So I want to just draw some functions on the board. And then I'm going to draw the integrals of these functions on the board. And my handwriting is really horrible. Sorry about that. But you probably know what to expect by now if you've been with me for a while. You don't expect greatness. You know I set the bar pretty low early on, so there's no reason to be disappointed. I'm disappointed in myself if that counts for anything. So there's something that all of these functions have in common. I'm not finished writing them, but at the end you'll see something they all have in common. All these integrals have just one key attribute in common. Awkward silence. All right, so this is the last of the integrals that I'm drawing right now. So I want you to just take a look at all of them and then see what they all have in common. So they all have a 2x in common. In all 6 of these integrals, we can see that there is a clear outer function and then a clear inner function within each composition of functions. So in all of them, in all 6 of these integrals, we can see that the inner function is always going to be 2x. In all 6 of these, 2x would be the inner function. The thing that differs between them would be the outer function. So we have sine of 2x, e to the 2x, cosine of 2x, so on and so forth. So we're going to use this as kind of a tool to help us understand the topic of today's video a little more clearly. Going to clean things up, make a little bit of space to work. So I want to take the sine of 2x. No, I want to take cosine actually for now. take cosine of 2x, and let's just review how to integrate something like this using U-substitution. So clearly our inner function is 2x. We always want u to be the inner function. So we're going to take the derivative, of course, as we always do. The derivative of u with respect to x, we're going to get just 2. Derivative of 2x is 2. And then we're going to perform a separation of variables. So we're going to have only du on the left side. We're going to move the dx to the other side by multiplication. Now this is what we call separation of variables. And then actually from this point on, notice how we have the dx in the integral. What we don't have in the integral is this 2 right here. So you're going to have to move that over to the other side. We're going to divide both sides of the equation by 2. So we're going to get 1/2 du equals dx. There we go. So now we want to go ahead and substitute everything in. So what I want to do is I want to replace 2x with u. This whole thing in the box is just u. And then I want to replace dx with something as well. I'm going to replace dx with 1/2 du. So let's go ahead and rewrite the integral. We're going to have the integral of cosine of 2x. I'm going to write cosine of u instead of cosine of 2x. And then I'm going to replace this dx with 1/2 du. And then we know with integrals, we can always move a constant to the outside. So I'm going to move the constant, the 1/2, outside of the integral, make things a little easier to work with, a little simpler. So now it's a lot easier. Now all we have to do is take the antiderivative of cosine, and we know that is definitely going to be a sine function. Antiderivative of cosine is sine. So we're going to get 1/2, and then we're going to replace u with the thing we already set it equal to. Instead of sine of u, I'm going to write the antiderivative as sine of 2x. I'm just putting 2x back in for u. 1/2 times the sine of 2x. And then, of course, we can see that this is definitely an indefinite integral. We don't have any limits of integration. So we're going to have that constant at the end. We're going to have that plus c. So we know that we did cosine of 2x dx. That was the function we're integrating. And we ended with this. So maybe there's a way we could just kind of naturally go from this to that without going through the busy work, all the steps every single time. It might be possible for us to develop some kind of skill that will allow us to do that. So in that, it is actually possible and positively easy. It might take some time to conceptualize the details and understand why this works the way it does, but it is a really, really fast, effective tool we can use to help us solve problems that would normally be pretty complex, especially when we get into maybe more complicated integrals, the trig stuff where you have to write things in terms of different trig functions using the trig identities. Chances are you'll be using a lot of U-substitution in some of those nested trig functions. So this is a really handy technique to have at your disposal, a really powerful tool to have in your mathematic arsenal. So we're going to talk about quick ways of going from this point right here to this one without doing any work. So how do we know what the constant's going to be out front if there is a constant? So I like to think of it like this. I already know what the derivative of the inside is going to have to be. So what if we didn't have the u and the 1/2 du and any of this stuff? So I'm looking at the inner function, and in my mind, I just kind of think, what is the derivative of 2x? The derivative of 2x, of course, is just going to be 2. And if we already had a 2 there, if they wanted to give us something easy to work with, they seldom do, but if they felt like it, if they gave us something like this, we'd be good to go. Derivative of 2x is 2, and hey, look, we have a 2 right here. Very nice, we're ready to go. But the problem is they didn't give us the 2 in this problem. So how do we counteract that? So we're going to have to divide by 2 in order to make things balance, in order to make the equation balance and make sure everything is equal just the way it is. So because we don't have the 2 right there, we're going to have to divide both sides by 2 of the derivative. So I just, in my mind, I picture it going like this. I imagine that du is going to have to be 1/2 du is going to have to be dx. And the du equals dx part is pretty self-explanatory. But this division by 2 just comes when we fail to have the derivative of our inner function. We divide by 2 just to counteract the fact that we don't have the derivative of 2x anywhere in the integral. And then I think to myself, well, we're doing a derivative here. With 2x, our inner function, we're doing a derivative here, and we're doing an antiderivative right there. So what is the antiderivative of cosine of cosine of x? Well, that would just be sine. Antiderivative of cosine is just sine. So we can do it just by thinking our way through the steps real quick. And it seems kind of confusing at first, but the more you do these, the easier it'll get. And yeah, I know I've done these problems so many hundreds of times that it just kind of comes naturally for me after a while. Like I said, this is my 4th time teaching Calc BC, and I've tutored calculus for, I think, probably almost a decade by now. So my point is, the more you do these, the more practice you get, the easier it will flow naturally. You'll get just kind of a natural intuition, and you'll be able to dive into problems like this and get the solution really quick without breaking a sweat before too long. Practice makes perfect. So we took the derivative, and that's where the 1/2 comes from. That's where this 1/2 out front of sine of 2x comes from, because we took the derivative and we don't have the derivative. So we had to counteract that by dividing the whole thing by 2. And then we took the antiderivative of cosine, and of course we just get sine. So that's where this 1/2 sine of 2x. And the plus c, we can easily tell that we do not have limits of integration. We don't have an a, we don't have a b, and whenever that's the case, we're going to have that constant at the end. We're going to have the plus c. So let's try that with a different function. Let's try that with e to the 2x. So what's the derivative of the inner function? Derivative of 2x is 2, but we don't have a 2 anywhere. It would be nice if we did, but we don't. So we're going to have to do what we did last time. We're going to have to divide by 2. So if we divide everything by 2, we're going to get 1/2 times the antiderivative. Remember that we're doing a derivative here, and we're doing an antiderivative here with our outer function. So we did the derivative already. What is the antiderivative of e to the 2x? That would just be, well, the antiderivative of the exponential function e to any power is going to be e to any power. So it's still going to be the exact same thing. Bam, we're done. It took a few seconds, and we found the antiderivative of a composition of functions. Ordinarily, we would have to do u equals blah, 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 du equals blah, 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 and then we would have to do some kind of a manipulation to account for the fact that we may or may not even have the derivative of whatever that inner function happens to be. We didn't have to go through all the steps. We got what we know to be the 100% correct answer just by working through it mentally, and we minimized the time it takes to do the problem. And that's why it's such a powerful tool to have at your disposal. Makes things much faster and much easier. Let's try that again with secant squared of 2x. So we're going to do the same thing that we did in the last few problems. We know that we're going to do the derivative here. We know we're going to do an antiderivative here. So what is the derivative of 2x? Well, just like before, the antiderivative of 2x is just 2dx, and it also works if we have other constants. What if this weren't secant squared of x? What if this were secant squared, for example, maybe 1/2 x? So we want to ask ourselves, what is the derivative of 1/2 x? Derivative of 1/2 x is just 1/2, but because we don't have a 1/2 anywhere in the integral, we're going to have to do something similar to what we've done in the past few problems. In the past, we didn't have the 2. So we divided both sides by 2 to kind of account for the fact that we don't have the derivative. This time, because we have a 1/2 inside, I mean, we don't have a 1/2 anywhere in the integral, we're going to actually multiply both sides by 2. So in the past, we divided both sides by 2. This time, we're going to multiply both sides of the differential equation that I'm picturing mentally in my head. Remember, we get a differential equation that's kind of like this. And in the past, we would divide by 2. This time, we're actually going to multiply by 2. So I just imagine this differential equation right here mentally. And that's how I can tell that we have to multiply by 2, when in situations that are kind of like that from the past, in the past few problems we worked on, we had to divide both sides by 2. So for this one, we actually multiply both sides by 2 to take care of the fact that we do not have the derivative of our inner function anywhere in this integral. All right, so we did that part already. Now what we want to do next is we want to take the antiderivative of secant squared of x, which is just tangent squared of x, or in this case, tangent squared of u. Let's do another one that's kind of like that. I think I'm going to set these aside for now. And then I want to come up with one that's kind of like this one. Let's say we have the antiderivative of cosecant of 1/5 x times cotangent of 1/5 x. I think I can write that a little neater. Dx. We want to approach this problem the same way we approached the last one. So it looks a lot different because we have two things being multiplied instead of one thing, but the process works exactly the same. So we're still going to take derivatives of whatever happen to be inner functions in this case. So in this case, we can clearly see that in both of our factors, the inner function is 1/5 x. So we're going to take the derivative of 1/5 x, and we're going to take the antiderivative of cosecant of a function times cotangent of a function. We could just generalize it and say this is just going to be a cosecant of u times a cotangent of u. So we want to ask ourselves, what is the antiderivative of cosecant cotangent of any variable or any generic function? That would have to be, well, we know that if it were negative, the antiderivative of negative cosecant times cotangent would be cosecant. So because we don't have a negative out front, we're going to have to add one there in the differential equation. So I'm imagining the differential equation in my head. I have a mental picture of what it looks like. So I want to take a look at this real quick, this 1/5 x. Kind of like what we did above. We had to multiply both sides of the mental differential equation, just have a mental picture of what that equation looks like in your head. And we knew we had to multiply both sides by 2 to account for the fact that we don't have a 1/2 anywhere in the integral. Same story applies with this one. We can see that we do not have a 1/5 anywhere in the integral. So what we have to do in order to account for that would be to multiply both sides of our imaginary differential equation in our head by 5. So I'm imagining this differential equation. I'm going to multiply both sides by 5. So that's why we're going to multiply everything by 5. But then I'm also going to multiply by -1. And that's just because the antiderivative of negative cosecant cotangent is cosecant. And because we don't have a negative right there, we're going to have to multiply both sides of the differential equation by -1 in order to take us there. So we have -5. And then the antiderivative of negative cosecant of x times cotangent of x is positive cosecant of x. But for our purposes, it's not going to be cosecant of x. It's actually going to be cosecant of whatever our inner function happens to be. So in this case, it will be cosecant of 1/5 times x plus c. So we didn't write down a u. We didn't write down a du. We didn't have to do any algebraic manipulation except what occurs within the safety of our own minds. And we got this. We were able to transform a really complex problem into something really easy we can do mentally. And if you're still not solid on this, I recommend just doing more practice of this method, and you'll get the hang of it before too long. You'll get it after a while. It took me a while when I was first learning these techniques, so it just takes practice. When you practice problems like this, your brain makes connections to things it didn't make before. It makes connections to things it didn't make connections to before. So practice definitely makes perfect. So let's try some more of these. Let's do sine of 2x. That's I think the ugliest, weirdest looking integral symbol I've ever made. So we have whatever happens to be the inside. Remember, we're going to take the derivative of that. We're going to take the derivative of 2x. We get a 2 for the derivative. And we don't have a 2 in the integral, so we're going to have to multiply or divide both sides of the differential equation by 2. So when we divide by 2, we get a 1/2. And then the antiderivative of sine is negative cosine. So we're going to have negative cosine of 2x plus c. That took seconds. We didn't have to write down a u. We didn't have to write down a du. We got the answer to this U-substitution problem really quickly. We just did it in our heads. Let's try square root of 2x. So for this one, you want to just mentally imagine that the radical is 1/2 power instead of a radical. We want to picture this in our minds as 2x to the 1/2 power. So we want to take the derivative of whatever happens to be the inside, just like with the last few problems we've done. The derivative of our inner function would be 2, and they don't give us a 2 anywhere in the integral. So we want to divide both sides of the mental picture of that differential equation by 2. Divide both sides of the differential equation by 2, so we get 1/2. And then we're going to take the antiderivative of the 1/2 power, which is going to be the 3/2 power, and then we're going to multiply that by 2/3, because if we divide by 3/2, if we divide by the new power we get, when we apply the power rule of integration, it would tell us to divide our result by 3/2, and dividing by 3/2 is the exact same thing as multiplying by 2/3. So our power is 1/2. When we apply the power rule for integration, we get 3/2. So we have the 2 and the 2 cancel out on the top and the bottom. So we just end up with this. We have 1/3 2x to the 3/2 power, and we're done. We didn't have to do any U-substitution steps on paper. We did everything mentally. And whoops, almost forgot the plus c. That would be highly embarrassing. I'm deeply ashamed, you guys. I'm sure if my calculus teacher from high school knew about it, she would kill me. She'd find a way to hunt me down and kill me. So that's how serious it is. So we just did this problem mentally. We didn't have to write down any steps. We're able to just think our way through the problem and get our answer in a reasonable amount of time. So that's why it's such a powerful thing to know how to do. And if you wanted, this isn't necessary, but if you really wanted to simplify this, we could maybe make this into square root of 2x and then that whole thing to the 3rd power. If you wanted, you can put the exponent underneath the radical, or you could do it like this. Doesn't really matter. And that's not even the main topic of the video. This isn't even necessary. The main topic is understanding how to do things mentally and get a result like this. All right. That brings us to our very last problem. And I actually don't really want to do it in this video because I found out that this is much more advanced than the other problems we've done in this video. So I'm actually going to be making a separate video on how to integrate this. So I hope you guys have found this useful. Hope you all enjoy the rest of your weekend, and I'll see you later. Bye-bye.